Welcome to my YouTube channel. In this video I will tell you about telescope, so let's get started. Telescope is undoubtedly the most important investigative tool in astronomy. It provides a means of collecting and analyzing radiation from celestial objects, even those in the far reaches of the universe. Galileo revolutionized astronomy when he applied the telescope to the study of extraterrestrial bodies in the early 17th century. Until then, magnification instruments had never been used for this purpose. Since Galileo's pioneering work, increasingly more powerful optical telescopes have been developed, as has a wide array of instruments capable of detecting and measuring radiation in every region of the electromagnetic spectrum. Observational capability has been further enhanced by the invention of various kinds of auxiliary instruments, example the camera, spectrograph, and charge-coupled device, and by the use of electronic computers, rockets, and spacecraft in conjunction with telescope systems. These developments have contributed dramatically to advances in scientific knowledge about the solar system, the Milky Way galaxy, and the universe as a whole. Commonly known as refractors, telescopes of this kind are typically used to examine the Moon, other objects of the solar system such as Jupiter and Mars, and binary stars. The name refractor is derived from the term refraction, which is the bending of light when it passes from one medium to another of different density, e.g., from air to glass. The glass is referred to as a lens and may have one or more components. The physical shape of the components may be convex, concave, or plane parallel. This diagram illustrates the principle of refraction and the term focal length. The focus is the point, or plane, at which light rays from infinity converge after passing through a lens and traveling a distance of one focal length. In a refractor, the first lens through which light from a celestial object passes is called the objective lens. It should be noted that the light will be inverted at the focal plane. A second lens, referred to as the eyepiece lens, is placed behind the focal plane and enables the observer to view the enlarged, or magnified, image. Thus, the simplest form of refractor consists of an objective and an eyepiece, as illustrated in the diagram. The diameter of the objective is referred to as the aperture. It typically ranges from a few centimeters for small spotting telescopes up to 1 meter for the largest refractor in existence. The objective, as well as the eyepiece, may have several components. Small spotting telescopes may contain an extra lens behind the eyepiece to erect the image so that it does not appear upside down. When an object is viewed with a refractor, the image may not appear sharply defined, or it may even have a predominant color in it. Such distortions, or aberrations, are sometimes introduced when the lens is polished into its designed shape. The major kind of distortion in a refractor is chromatic aberration, which is the failure of the differently colored light rays to come to a common focus. Chromatic aberration can be minimized by adding components to the objective. In lens design technology, the coefficients of expansion of different kinds of glass are carefully matched to minimize the aberrations that result from temperature changes of the telescope at night. Eyepieces, which are used with both refractors and reflectors, see below reflecting telescopes, have a wide variety of applications and provide observers with the ability to select the magnification of their instruments. The magnification, sometimes referred to as magnifying power, is determined by dividing the focal length of the objective by the focal length of the eyepiece. For example, if the objective has a focal length of 254 centimeters, 100 inches, and the eyepiece has a focal length of 2.54 centimeters, 1 inch, then the magnification will be 100. Large magnifications are very useful for observing the Moon and the planets. However, since stars appear as point sources owing to their great distances, magnification provides no additional advantage when viewing them. Another important factor that one must take into consideration when attempting to view at high magnification is the stability of the telescope mounting. Any vibration in the mounting will also be magnified and may severely reduce the quality of the observed image. Thus, great care is usually taken to provide a stable platform for the telescope. This problem should not be associated with that of atmospheric seeing, which may introduce a disturbance to the image because of fluctuating air currents in the path of the light from a celestial or terrestrial object. Generally, most of the seeing disturbance arises in the first 30 meters, 100 feet, of air above the telescope. Large telescopes are frequently installed on mountain peaks in order to get above the seeing disturbances.